All right. The other big concept is the octet rule. So the octet rule is talking about how everything wants to look like group 18, right? Um, Elements want full valence shells. All right, that is the key concept here. Group 18 starts with full valence shells. So group 18, the noble gases, these guys are what we call stable. Um, they're stable and their charge will be 0 because stable means they don't want to change. They don't want um, to lose or gain electrons, right? They won't have a charge. Everything else, right, we do kind of disregard these for our purposes. In higher levels of chemistry, you will not disregard them, but we are. Everything else wants to get to group 18. And essentially, the octet rule describes that they want to take the shortest path there possible. Let's use fluorine, for example. Fluorine has 7 valence electrons, right? So valence electrons you count by starting here in the row that they start in, and you just count to their place. So fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. Fluorine wants to gain 1 electron to complete its octet. All right. When it does that, it becomes a negative ion. It becomes an anion because it's a non-metal, right? But it does that because it's just one step away. It needs to gain 1 to become to have an electron configuration that looks like neon, right? That has a full valence shell. So group 17, they'll have charges of -1. Oxygen, right, in group 16, these are 2 steps away. So they need to gain 2 electrons. They'll look like -2. Group 15, they're 1, 2, 3 steps away. So they'll look like -3. Group 14, they're 4 steps away. So they can either be a plus or a -4, depending on the context. We'll learn more about that when we talk about bonding. Group 13, you might think that they are 1, 2, 3, 4, 5 steps away, right? So you might think that they would have a -5, but it is much easier for, let's say, aluminum. So aluminum's configuration looks 2, 3, 4, 5, 6, 7, 8, like this. So aluminum could gain 5, or it could just lose 3 electrons to then look like this. 1, 2, 3, 4, 5, 6, 7, 8. We have a +3 charge. So since it's less steps to go backwards and lose electrons, that's what these guys will do. Same with group 2, same with group 1. You can see here that when things lose electrons, they become positive. The ion is smaller than the starting atom. And for negative ions, the ion will be larger because the extra electrons will repel each other more and push the atom apart a little bit. On top of that, for reactivity, reactivity is essentially how fast, for our purposes right now, you can think of it, it's how fast something will become an ion. And you can kind of think of it like elements are more excited when they are fewer steps from group 18. So what I mean by that is that in our review, one of the questions was comparing 16 and 17. Group 17 is more reactive than group 16 because group 17 is only one step away from group 18. That also relates to their electronegativity, right? Group 17 is more electronegative than group 16, meaning that they will gain electrons more quickly. On the flip side, metals don't like to gain electrons, right? Metals like to lose electrons. So, like if we compare group 13 to group 2, group 2 only needs to lose 2 electrons. Group 13 needs to lose 3. So this group 2 will be able to lose its electrons faster and get to group 18 more easily than group 13 will. That is what causes group 2 to be more reactive than group 13. That also relates to trends in ionization energy. These guys have lower ionization energies. It takes less energy for them to lose their electrons, which means that they are going to more easily become ions and react in order to do so.